because there's one piece of information that's being missed on this, and that's how to draw in your axial and equatorial positions. Okay, so I'm going to draw the backbone of our chair just in black all the way through this, and then I'm going to add in the proper places to put your axial and equatorial positions, okay, theoretically. Okay, and we'll talk about some ways that you can kind of dodge around that. So we would start with our seat. That's not black. Let's try that again. 2 staggered lines. From the short line, draw up. Short line, draw down. And we now have our chair. Okay. Again, for frame of reference, our chair is facing to the right. Okay. So if you sat in that, that's where you would be facing in the standard view. The next part comes into this issue of axial versus equatorial. Okay, so we talked about where those atoms are located, or where those bonds are located within a structure. And this gets kind of a bit tricky to deal with. Okay, so our axial positions, for lack of a better description, are on the axis. No response, huh? Okay. They're on our axis, usually going up and down. Okay. So I could go through and I could draw up. Okay. Is that an axial position? No. So it's not just up and down. We have to have the proper frame of reference. Okay. And this is where this is going to get a little bit weird. It's up and down. Whoops, that's an eraser. In the direction, I'm going to call this of the point, okay, or our triangle. So if we go to that exact same position, what I'm referencing is this point, or that kind of triangle. Where is that point aiming? Up or down? Down. Where's my axial position? Straight down from that point. I want to clean that up a little bit. So our axial is now straight down. You'll notice that in most circumstances that we will draw a break at that line and then make sure we can put our group down here. And I'll label that as Ax for axial. Why do we include that break in the bond? That's behind the plane of our board, okay, or the plane of our drawing. It's behind that carbon bond through the front. Okay, so we're trying to show that break and imply its relative location. It's not necessary, but it typically shows up. Okay? If we move to another point, let's look at this one. Where's that point largely aiming? All right, it's largely aimed down. So where's our axial position? Down. Okay. What about this point? Where's that largely aimed? Okay, up. It may not be super obvious, and it depends on how you draw your chairs that you may end up not seeing this. So we put that again straight up, and that's our other axial position. So you should be able to go through at each of those vertices and drop in an axial bond. Does everybody see those axial positions and think that you could go through and draw them on your own? I think I'm hearing yeses. Now the challenging one. Your equatorial position. The equatorial is not easy to draw. Okay? And as far as a definition goes, okay, the best way for me to describe it is not axial. Okay? The axials are very clearly on this up-down axis. Your equatorial ones are not on the up-down axis. Okay? And if you looked at the model, they'd kind of be in the plane of the ring. Okay? Well, we've got this drawn where we don't really have a plane of the ring, so that becomes difficult to see. Okay? So let's pick this carbon here. The axial is aimed directly up. So where should the equatorial be? Down. Okay, but if I draw it down, at least the way I've got this set up, can you see where I drew it? No. So it becomes a little bit difficult to pick out. So where the equatorial gets drawn is here. That is our equatorial position. So it is still down, right? And it is also very clearly not axial. It's not on that up-down axis. Okay? It's kind of off to the side, a little slanted. Another position, okay, particularly one that's more difficult to draw. That one in there. Right? Our axial is aimed straight down, so our equatorial needs to be up. But if we draw it up, it looks like it would be axial, right? Okay, if I just draw that straight in there, now that looks kind of like an axial position. Okay, and in that position, you're right, it is going to be very confusing to identify that position as axial or equatorial. That's why when we defined our axial, we said aimed direction of the point. And that line that I've just got drawn in there, is it aimed the direction of the point? No. Okay, so it is completely opposite the axial. If you drew it like this, this is still technically not correct. Where it should actually be drawn is here. Okay, so those are our two equatorial bonds drawn in there. Yes?
Would it matter if you drew it like more to the right than the left?
So this gets into how we should go through and draw these. So our axials, we picked the point, and we just went up and down directly off of that. So we at least had a reference. Our equatorial definition right now just says not axial. Well, that's a pretty crappy definition. Okay? There is a specific location on where the equatorial should be drawn. And it is not axial, but it's also relative to something else. Okay? Your equatorials are not axial, and they are parallel to the second bond away. Okay, so let's pick the weird looking equatorial up at the top. We're going to start with that guy. Second bond away. Here's 1, here's 2. If you take a look at the equatorial bond and that second bond, is it parallel? I mean, at least to a first approximation, that's pretty darn close. Okay? But that was counting left to right. Of course, it's got to be different if we counted right to left, doesn't it? It's also parallel. Doesn't matter which direction you count around your structure, it will be parallel to it, assuming you drew the chair nicely. Okay? So this is where picking up some skill in drawing chairs can help you nail these down a little bit better. Okay? So this gets to your question of to the left or to the right. According to where we want to draw our equatorial, it needs to be parallel to the second bond away. If we drew that line a little bit more to the right, is that parallel to the second bond away? No. So it doesn't fit our rule set for where it should belong. Okay? Why get kind of nitpicky with this rule? It's a selfish reason. If you go through and draw out a chair on an exam, what do I have to do with it? I have to grade it. And if you don't have your axials and equatorials in the proper location, I look at it and I have no idea what you've drawn. And if I don't know what you're drawing, I take off points. Okay? So you want to be as explicit as possible when you set up these drawings to make sure that I can go through and grade it appropriately. Okay? My favorite bond to see on an exam, we'll call this one in blue. So if we look at that point down here, is I've seen something like this. Okay. What one is that? Is that equatorial or is that axial? That blue bond. It's confusing as all hell. And as a grader, I would be like, I don't know what you're trying to draw. You don't get any points. Okay? Let's say you wanted it to be equatorial. What could you add to this to be like, no, dang it, this is equatorial, not axial? You could, so there's a couple options. You could draw one straight down. The straight down one now fits our axial rule, which means the other one must be equatorial. I do have the logical wherewithal to kind of pick that off, but I'm fully aware that as a student we can be a bit wily and we might do something like this. Now both of them don't look axial, and I still have no idea what you're trying to do. Okay? So under those circumstances, one of the best ways you can go through and do it is add more information. Okay? If you want that to be equatorial, what should you write? EQ. Okay? Now I know you're saying it's equatorial. I'll accept that. I won't be happy with it because you drew it in the complete wrong spot, but you at least acknowledge that you know that it needs to be equatorial. I can now attempt to grade that.
Which one are you comparing it to, though?
What do you mean?
When you draw it's parallel to the second bond away.
So let's draw in the equatorial position appropriately for that carbon. Second bond away, so we're starting from this carbon and we want to draw in our equatorial. We either go 1, 2, or we go 1, 2. So we need to be parallel to either of those two bonds. Where's parallel? There. Why would I not draw it down here? Because that's aimed down. Where's the axial aimed? Where's the axial supposed to be aimed? Down. Okay? Your axials and equatorials will aim opposite directions. So that other line doesn't make sense to draw it down because that's where the axial is supposed to be. The equatorial is not axial. Okay? Kind of makes sense? It takes practice to draw these. You will probably only have to draw them on this exam and not any other future exams. Maybe. I can potentially see it showing up on exam 3. So if you just decide that you can't draw them, then just accept the loss of points and move on to a different question. Okay? But what we're trying to set you up with is the rules to go through and draw them appropriately. Questions with that?
I'm not seeing why it should be pointing up and not why the left side is invalid.
What is the axial position aimed? Where does the axial need to be on this? Down. Where is the equatorial? Not axial. So if the axial is aimed down, where does the equatorial need to be? Up. So if the left line is aimed down, that doesn't make sense. Okay? Because you're putting it in the same plane as your axial. Okay? Questions? Sorry, go ahead.
Does it matter whether we draw the chair facing to the right or facing to the left?
Depends on the question asked. Okay? More often than not, it does not matter which direction you're aiming your chair. What will probably get asked is you to draw 2 chairs. Okay? One facing right, one facing left. Okay? Potentially. In a lot of the permutations that you'll be asked to go through and draw, both in the homework and potentially on the exam, we'll ask you to do a ring flip. Okay? In a ring flip, we take the head, where we rest our head, and we turn it into feet. And we take our feet and we turn it into a head, which changes the direction of the chair. Okay? What you may notice is that you can go through and do that, but still draw the same chair. How can you do that? Not quite turn your paper around, but the right idea. You change your view on the molecule. So you do the chair flip and then you turn the chair. Okay? I do not recommend that. Okay? If you happen to luck into it and it works, great. The issue with that is that if you do a chair flip and a rotation, more often than not, you don't realize you did the rotation and you're drawing the wrong structure, which is chapter 5. Okay? So be careful with that kind of approach. Big lessons from yesterday when we were talking about our chairs. Our axial position is what? What do you know about the axial position? Less stable, which means, yep, there's the other conclusion, higher energy. So if we look at an individual structure, we're going to look for our largest group, and we want that largest group to be located where? In the equatorial position, because our equatorial position is more stable because It is lower energy. I just swapped the order of those two. Oh, no, I didn't. Good. Okay, questions about that? Deep breath, awesome fun, quiz. Again, we've got those CH3s on the same side of that ring. Everybody's okay with that? Then what I noticed, people went through and said, well, if I want the lowest energy conformation, they need to be equatorial. Okay, so we go to the chair, and I now draw them in equatorial. That is absolutely an exceptionally low energy chair. Is that the cis-1,2 structure?
No.
Okay. What we've got drawn in that chair is the trans structure, not the cis. So this question gets to nomenclature and it gets to energetics within Newman projection, or not Newman projections, within chairs. So it's a complex question that asks multiple stages. You have to make sure your answer satisfies all of those conditions, not just the one that you want to answer. You have to make sure that every single piece of information provided to you matches. And in this case, if we had asked for specifically on the exam the cis-1,2 dimethyl, and you give me that chair, you're wrong, because you didn't draw cis-1,2 dimethyl. What you drew was trans. What do I need to do to make it cis? One has to be aimed the other direction. So since this topic is depressing, let's go ahead and just say it's down. Right? Downer. Which means that CH3 is now located where? Axial. And the other one is located equatorial. And I'm out of space. Let's just say hello. Is this now the lowest energy chair? Okay. What do we have to do to go through and test this? We'd have to go through a chair flip. So if you aren't sure, go through and do the chair flip. What once was your feet becomes your head. And as we do a chair flip, what was axial becomes equatorial. And we look at our other carbon is in back now. What once was equatorial becomes axial. Which of these chairs is more stable? They're exactly the same. Okay? So if you pick that one, you could have drawn any chair as long as you had that cis accuracy right. There was only one chair to draw. Okay? Is this true for all of these? No. Okay? So what you should go through and do is test the other positions. Okay? Both cis and trans. You'll notice that I only gave you 1, 2, and 1, 3. Why did I not give you 1, 4? 1, 4 is the same thing as our 1, 2. Okay, we get the same result. Why did I not give you 1, 5? Well, nomenclature-wise, actually, that's why I didn't give you 1, 5. But it gives you the same thing as your 1, 3. Why did I not give you 1, 6? Again, we run into this nomenclature issue, but it's the same thing as 1, 2. Okay? So you should check arranging those around an individual structure and see what happens when you go through and draw these out as chairs. And verify to yourself what's happening. Do you have a lowest energy chair? Do you not? Okay? It's a bit tricky and it takes some time, but that's ultimately going to solidify the concept for you and allow you to really understand and look at a whole bunch of different problems. All right? Yes, Michael.
So I wanted to know if you have a specific order to remember the carbons measures.
Is there a specific numbering behind the carbons? Not yet. It doesn't really matter how we go through and number these, at least at this stage. Okay? What we will find is that that numbering does become important when we move into Chapter 5, which is just about to happen. Okay? And as long as you number consistently, you're okay. Okay? So if I was going through and looking at this, if this is carbon number 1 and this is carbon number 2, where's carbon number 1 in my overhead view? Let's be hot or cold. I'll start here. You can tell me when to stop for carbon number 1. Good. That's carbon number 1. That's carbon number 2. Okay. If you swap the order of those two in this specific problem, it doesn't matter. If we had a trans conformation, it does. Okay. So you do have to be a little bit careful with that numbering system when you go through and draw a chair from an overhead view. In this case, you were drawing them both, so you could be consistent in both cases. Okay? Fun, exciting stuff. Okay. Tail end of chapter 4, you get the Haworth projections or Haworth projections. It's a relatively minor contribution to our overall class, but you will see it pop up every so often. So when we look at a cyclohexane or even cyclopentane or any of those, okay, with the cyclohexane, we've got the 2D overhead view. This gives us our up-down alignment. So we could draw in wedges and dashes over the top of this, right? Okay, we can say, oh, that one's coming at us, that one's going away from us. We can move to a 3-dimensional side view, and that's our chair. So we've got an implied 3 dimensions within that without showing our wedges and dashes. This really gives us information about our axial and equatorial. We could also go through and shift to a 3-dimensional end view, which is our Newman projection. This really gives us conclusions about energetics. All right, so depending on what we were asked, we may decide to look at varying ways to draw these. There's yet another way that we could possibly draw out our cyclohexane structure. It's referred to as a Haworth projection. What we're doing is taking our 2-dimensional structure, our 2D overhead view, and I'm now turning it so that I'm looking at it from the side. Right? You will almost always notice that your Haworth projection has implied, or not implied, but actual wedges and dashes, wedges drawn into it. Okay? So what we've done is taken that cyclohexane flat structure, and I've now just kind of pulled it out at you. You're looking at it from the side. What that does is the wedges and dashes that we had on our 2D overhead are now very clearly going either up or down on our Haworth projection. So we could go through and say that, uh-oh, what happened? Nothing. Okay. We have an up position and a down position here. So if I put a CH3 here and a CH3 over here, what is the relationship between those two CH3s? Opposite sides, which means trans. Okay. Not anti. Anti is our Newman projection stuff. Okay. So that's the only deal with this. All we're doing is turning it on side. Okay. This gives us a slightly different viewpoint of the molecule, and depending on what we're trying to do or evaluate, it may be easier to see our result in the Haworth projection than all the others. Okay. That's really the only reason it's mentioned. Okay. Where it becomes super important is in a structure like this. Anybody recognize that? It's a disaccharide. It's a famous disaccharide, theoretically. It's normal sugar, our sucrose. Okay? So when you think about biochemistry and sugar molecules and carbohydrates, you're looking at Haworth projections. Okay? It's just a slightly different way to look at the molecule. This was easier for them to evaluate as opposed to drawing out the chair conformations for a structure like that. Okay? And you might agree that looking at it in the Haworth projection is easier than drawing out a chair for something as complex looking as this. Okay? If you don't agree, draw the chair and then talk to me. Still, nothing. Okay. Is this on? Topics that you need to review on your own. There's all sorts of stuff popping up in chapter or section 4.4 talking about different names for strains and energies. There's torsional strain, there's angle strain. I don't really care so much about the names of those, but that you understand that they have an effect. For instance, your angle strain. We have an angle strain in a cyclobutane. Why? What's the bond angle in cyclobutane? 90 degrees, but that carbon is sp3 hybridized, which means the bond angle needs to be 109.5. There's an angle strain. We've crunched that angle down tighter. Your torsional strains. Okay, your torsional strains are ultimately coming out of Newman projections. If we put two large groups next to each other, there's a torsional strain by having those two there. What do they want to do? They want to torque away from each other. So we've got a torsional strain. Okay, I think. I never actually bothered to memorize what the names actually meant. I just looked at, hey, that's bad. Okay, which is really all you need to get out of it. In section 4.5b and c, they talk about propane, butane, and pentane, the general shapes that come out of that, and they talk some more about some of the strains that come through those. Okay? Not that big of a deal, but it is something you should kind of be aware of. Okay? 410 to the end of the chapter talks about using models, which, if you hadn't guessed yet, you should be using models. Kind of important. Talk about constitutional isomers, which we'll talk about today. And then this IHD, which I've referred to previously as the degree of unsaturation. It's also known as the index of hydrogen deficiency, because we don't have enough big words in our language that we need to make some other stuff up. Okay? The IHD is a representation of how many rings or pi bonds are in the structure. For every degree or single index unit, you have a ring or a pi bond. You'll notice it says pi bond, not double bond. Because if we said triple bond, well, that becomes a bit problematic, because a triple bond isn't a double bond, it's not a ring. So what's its degree of unsaturation? Well, according to that definition, it wouldn't have one. It's pi bonds, though, not double bonds. How many pi bonds are in a triple bond? 2, which means its index of hydrogen deficiency? 2. Okay? There's a nifty little formula that you can use to go through and calculate this if you so felt. We'll talk about it a little bit more when we look at mass spec, okay, which is in our spectroscopy chapter next week. So we've got that fancy little formula, 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens divided by 2. Okay? Yeah, it's this big, long, drawn-out, stupid formula, and it's really pretty meaningless. Okay? But you will probably see questions in the homework on it, just getting you to work with it. You probably do not need to spend any time memorizing it. Depending on who you talk to, they actually ask that you memorize that. I'm not one of those people. Yes?
Would that other question be in the final exam? Most likely.
I don't believe it's asked in this fashion. Okay. Really what you're primarily concerned about is one ring, one pi bond. Okay. One ring or a pi bond when you're coming through and dealing with this. When we look at mass spec, that's where it shows up a little bit more in depth, and there's ways that we can dodge that to avoid having to worry about it. Questions? Awesome. Chapter 5. Chapter 5 really centers on this one special little molecule here, known as thalidomide. Has anybody heard of thalidomide before? Okay, a few people, maybe because you read the activity, the model lab activity. Okay. It was a pretty awesome drug when it came to curing morning sickness for pregnant women. It was phenomenal. It was in the late 50s, early 60s, about that time when it was commonly used. And it was prescribed out the yin-yang to everybody so they didn't have to worry about being sick. Right? Well, it cured morning sickness, but then when it came time to give birth, they noticed that a very high percentage of the babies that were born from mothers that had taken the drug had birth defects. Right? Massive birth defects. Right? And they couldn't quite figure out why. And eventually it came back to this drug, and it really centered all about this carbon. Okay, that carbon right there. So there's a new notation showing up here. You notice there's that little weird squiggly line? What that squiggly line means is that we have not specified whether that is a wedge or a dash. Right? Well, we think wedge and a dash, that doesn't mean much. All we did is turn the structure around. Well, not officially. It turns out that if we make that a wedge, we draw the exact same structure and make it a dash, that those two structures will never superimpose. Right? And it turns out that one of those forms, okay, was awesome at curing morning sickness. The other form, when it decomposed in the human body, turned into a mutagen that caused all the mutations to then do the fetal things, babies, fetus, one of those words. The thing, the parasite inside the woman's belly. Okay? So it was kind of with this drug that this whole kind of understanding of chirality really took shape, and we said, okay, this is actually something that's important that needs to be studied. Okay? And it is exceptionally difficult to wrap your brain around, which is one of the reasons why we ignored it for so long. And then we found out it's actually important, so now we got to teach it and talk about it. Okay? So what's happening with it? We come across these two words, chiral versus achiral. Okay? All structures potentially have a handedness to them. Some of them are ambidextrous, if you will. So both hands kind of overlap, and we don't really have a preference of right or left hand. Okay? Those molecules are achiral. And molecules that are chiral have a specific handedness associated with them. And it's kind of a weird phrase. And what we're coming back to with this handedness is that your left and your right hand are chiral. Okay? And what that's really saying is that our definition of chiral is that they are non-superimposable on its mirror image. And we've talked about this in class too. Well, you just take your hands. Oh, they're superimposed. Right? You're not superimposing the top with the top. The top of your hand must overlap with the top of your hand. And there is no way that you can do that. Okay? It doesn't happen. That's what you get for taking notes. Not watching me. Okay? You don't get that even overlap. Okay? An achiral molecule will superimpose on its mirror image. So we've got two examples down here. We've got a chair and we've got the hands. Well, we just gave away the answer on the hands. Our hands are chiral. What about the chair? So we look at a mirror image for a standard chair. It does superimpose across it. Okay? So the chair is achiral, and your hands are chiral. Okay? Thalidomide was our big drug. This is where we had this issue. Okay? It's what really brought this to the forefront because thalidomide is a chiral molecule. So what we ended up doing was evaluating the different states, and we really kind of centered on that carbon. And that carbon has a particularly interesting arrangement around it. It's got a carbon, carbon, nitrogen, and hydrogen attached to it. Those are four distinctly different atoms. Okay? And it gets a little bit weird because is there a difference between carbon and carbon? No, but can I tell the difference between those two carbons? Yeah. So they are distinctly different even though they're the same element, but they have different bonding patterns around them, which makes them different. Okay? That then brings in a special attribute to that central carbon so that if I drew out its mirror image, it is no longer superimposable, or it can't superimpose on it. Okay? So it's kind of a bizarre feature. Particularly with a structure this big, how would you go through and do that? Well, you have to draw out the mirror image of it. It's a bit difficult to go through and do, but that's kind of what you're expected to do with some of our molecules. So in chapter 4, we had this big sequence of relationships all the way through it. Okay, and you'll notice that I've added an extra little pattern up here. We got a different sequence of molecules up top. Okay, so what we want to do is come up with the relationship between those molecules. Do they have the same molecular formula? Yes. Are they superimposable? Not like that. What do you mean? Okay, so we have to take the molecule, let's say on the right, and flip it over. Then the carbon backbone would overlap, right? Everybody see that?
Correct.
Okay, so if we flip it over, chlorine's wedge, the chlorine's wedge, doesn't that superimpose? If we flip that structure over with the chlorine wedged, and I now flip it over, it's going to be dashed. It's going to be aimed the other direction. So while the carbon backbone may now overlap, the chlorine does not. So they're non-superimposable. Okay? That puts you now in this category of isomers. And we run into the question of, do they have the same atom connectivity? Okay? Yeah. That drops us into this stereoisomers. Okay? And one of the approximations that I think we talked about is we could look at different names versus same names. Since you've been working on nomenclature, those two structures would have the same name, at least as far as you guys know at this point. Right? If they have the same name, we're looking at stereoisomers. Well, stereoisomers can be further subcategorized into some other relationships. Right? So we want to be able to find if we have stereoisomers. And one of the big characteristics to look for is asymmetry. If we have an asymmetric molecule, we're going to have a chiral molecule. And if it's chiral, we're now looking at that enantiomer category. Okay, so we've seen these before, geometric isomers with double bonds and rings. Okay? Those compounds are not going to be superimposable on each other. If we look at their mirror image, sorry, not quite, it's not that. These are geometric isomers, not our chiral molecules. So our stereoisomers will subcategorize into chiral molecules and into geometric isomers based on whether or not they have a chiral atom within them. And that's a trickier thing to look for. In our geometric isomers, they would be classified as stereoisomers, but they don't have a chiral atom. So where do we find a chiral atom? Well, a couple things can pop up here. We've got some examples. So I've got two models in my hands right here. If we take a look, there it is. They are mirror images of each other, yes? Everybody see that? So the mirror is running directly through the middle of this. Right? Are these superimposable? Are they superimposable? Yes. Right? So we'd say, okay, achiral. We're not looking at a relation to stereoisomers. But what happens if we change this, and bear with me, use some of your imagination. Blue and brown both begin with the letter B, so we're going to say those atoms are the same thing. Stupid little balls. No inappropriate comments there, guys. So there we go. Are these mirror images of each other? Yes. Are they superimposable? Right. If we spin this around so the brown overlaps with the blue and the green overlaps with the green, they're non-superimposable. Okay, well, what changed? What happened when I went to this model set versus the previous model set?
The carbon is attached to 4 unique.
I'm looking at a carbon, that center atom, having 4 unique things attached to it. If I have a carbon with 4 unique things attached to it, I have a chiral center. So when we look at the mirror image, it will be non-superimposable on that mirror image. Does it have to be a carbon atom? Could it be a nitrogen? Yeah. A nitrogen could possibly have 4 different things attached to it. So nitrogen could potentially do it as well. Okay, so it's not unique to carbon. Why do we focus on carbon? It's organic chemistry. Everything we're working with is typically carbon. Right? So what we're looking for is that asymmetry, and that asymmetry is typically found in a chiral atom. The other thing we could look for are planes of symmetry. So if the asymmetry is too difficult to look for, maybe you should look for symmetry. Right? So if we took a look at the first model that I had, where we had 2 hydrogens on it, is there a plane of symmetry within the molecule? Okay, well, of course, our picture up on the board shows that, but there was our original molecule. Where's the plane of symmetry? Right down the middle, where we split the green and the brown atom directly in half. There's a plane of symmetry running down that axis. If we have an internal plane of symmetry, the molecule must be achiral. Okay? Is it easy to see an internal plane of symmetry? Hell no. Okay? It's one of the reasons why I tend to not talk about it as much. Okay? If we take a look at the 2 structures shown in the middle, do these have internal planes of symmetry? All sorts of tricky things are happening within this. Stick with the bottom one. Where's the bottom one's internal plane of symmetry? It's the plane of the paper. Okay, splitting all of your carbon atoms directly in half. That is your plane of symmetry. Not easy to pick up and see, but it is there. Okay? Where's the plane of symmetry for the next one? Why is it not running through the plane of the paper, splitting the carbons in half and splitting the bromine in half?
Because the hydrogen's on the other side.
Remember that pesky little hydrogen that we were talking about? You got to watch out for it. Why is that important? Take a look at that carbon. How many bonds are shown? 3, which means there's an implied hydrogen, which means that bromine is not in the plane of the paper. It's either coming at you or going away from you. You can't split the bromine in half. So you have to be careful when looking at your structures, because maybe we've been nice and given you the wedges and dashes so that you can trigger and say, oh, there's a chiral molecule. Or maybe we haven't. Okay? So you have to watch out for that hybridization, okay? And those implied hydrogens. Let's take it a step further to one more little fun example. It's usually an obnoxious one to deal with. Let's take a look at that ring structure down at the bottom. That was a horrible looking wedge. I'm making this a wedge. What is this compound? Cyclopentane with a methyl, so we're looking at methyl cyclopentane. Is this molecule chiral? What did we just talk about with that upper example? What did they say we needed to see? Help us out, see like a wedge and a dash, and we go, oh yeah, there's a chiral molecule. What do we have in this bottom one? You got a wedge.
There's also a dash.
Okay, there's also a dash, but what is that dash to? Hydrogen, so that's different. Where's the internal mirror plane in this one? Not through the plane of the paper. It's perpendicular to the plane of the paper. It's coming directly out at you. We're now splitting the hydrogen and the carbon atom in half. Okay, there's your plane. Okay. So why did we show the wedge there? Because one of the natural tendencies for students is they see a wedge and they go, chiral. No. It has to do with that internal mirror plane and is it superimposable on that mirror image. So you have to be very careful when looking at your structures that you don't fall for fake wedges and dashes. Okay? And that you don't fall for hidden wedges and dashes. Okay? So be careful when you're evaluating these kind of things.
So what is that?
Whoops.
So that was achiral?
That is achiral. Yes?
So would pi bonds also affect it then?
Pi bonds can also affect it, but if we draw a pi bond through, so this is where we run into that chirality issue, that they are still achiral. Okay? It may be a stereoisomer, okay, but it's not. But it's going to be achiral because where's the internal mirror plane in the pi bond? It's the plane of the paper. Okay, so your plane of paper makes that achiral, but it is a stereoisomer.
But if it was in like the cyclopentane?
If it's in the cyclopentane, then you're absolutely right. It does make a difference. Because now when we go through and look at this, do we have 4 distinguishable groups around that center carbon? Okay. We've got a CH3, an H, a CH2, and a CH. Are those all distinguishable? Yeah, now we do have a chiral atom. Oh wait, that's a 5-bonded carbon. Never mind, let me draw this. I gotta draw the double bond somewhere else. There. Okay, now we have a chiral atom. Yeah. And it is that blue carbon. I heard you mumbling the 5-bonded carbon, but I didn't listen. Sorry. Hearing without listening. I'm a horrible person. So, stereoisomers, what happens with these? Okay, so as soon as we bring in this concept of chirality, we end up with some new definitions or some new words that pop into this that we would need to include into our flowchart. Okay? We get enantiomers. Enantiomers are structures that are non-superimposable and are mirror images. So if we take a look at two structures, we're comparing two structures again. And we look at those two structures and we say, oh, they're mirror images of each other. Okay? Are they also non-superimposable? If they satisfy both conditions, the relationship between those structures is that they are enantiomers. Okay? Next one is particularly fun. We look at two structures that are non-superimposable again, but this time they're not mirror images of each other. Okay? Under this circumstance, we've got diastereomers, or as students typically like to call them, disastermers. Either's fine, I don't really care. Okay? The last one, a mesocompound, okay, this one's got all sorts of fun definition things with it, is a structure that has two or more chiral centers and is superimposable on its mirror image. That's a bit odd, because it is superimposable. Okay? One of the big red flags for a mesocompound is finding an internal mirror plane, you still have to find those two chiral atoms. So if you have an internal mirror plane and two chiral atoms, at least two, you've got a mesocompound. So let's stack this into this. So yeah, of course it's got to get smashed a little bit. Where we ended before was up at our stereoisomers. So our new additions. Identical. If you have two compounds that are superimposable on each other, look for two chiral atoms. If you have at least two chiral atoms, it's a mesocompound. Right? If we move to stereoisomers, if there's a chiral atom, then we move over to another set. Right? If there's no chiral atom, we're looking at geometric isomers. This is largely your cis-trans, and really only going to center around pi bonds, double bonds. Right? Just a second, let me finish the way through. If we do have a chiral atom, then we have to ask ourselves, are they mirror images of each other? If yes, then they're called enantiomers. If no, they're diastereomers. Okay? These questions are kind of crappy, because what it'll be is here's two structures and here's a list of 4 possible things. Okay? You have to go through and decide which of those 4 possible things match. Do you get a flow chart on the exam? No. Okay, so you have to be able to evaluate this. If this is something that you want to try and cram for and get this memorized as quickly as possible, get your exam, and as soon as you've got the exam, you write down the little flow chart, that's fine with me, I don't care. All right, you can get that purged out of your head as quickly as possible, because it will be easy to forget. Okay, yes?
So, to have more than 2 chiral atoms, are you saying the third one is going to be cut in half on the plane for it to be?
Let's move to an example. Okay, so if we take a look at this compound, okay, how many different ways can we draw this compound? Okay, there's a big issue here. What's the hybridization of both of these carbons? sp3, which means there is an implied hydrogen on both those carbons. Okay. What we could then go through and do is look at all the possible permutations of wedges and dashes. You may panic, oh my gosh, all the possible permutations. It's not that bad. Okay, so what I like to do is not draw it so big. Let's try that again. Is go through and just pick one atom first. I'm going to say this one here. I'm going to make this my wedge for my chlorine, which means that one's dashed. Or it could have been the other way around. Whoops, that should be an H. And my chlorine. Now what I'm going to do is shift the other direction to the side. I'm going to maintain the geometry at that first one. So there's my wedge for my chlorine. And my other position now could have been wedged chlorine. Or it could have been dashed chlorine. What happens with the other option? go up to the top one, we do the same thing. I'm going to have my chlorine, I'm going to maintain that one the same, but now my other option, it could have been wedged chlorine for that one, or dashed chlorine. I've now covered all possible structures, right, by being very methodical in how I organize this. Right? Which now gets us to this question of finding stereo, well, not quite to your question of finding stereocenters. We'll approach that in just a second here. Okay? If we now want to look at the relationship between these, we'd have to go through and look at all of these four things and say, okay, what's the relationship between this one and this one? This one and this one, this one and this one, this one and this one. Okay? So what's the relationship between these two? I know, you guys memorized that slide already, didn't you? Okay. So we're going to slide all the way into the stereoisomers category. Okay. We could look for a chiral atom. Our chiral atom has four distinct things attached to it. So we got chlorine 1, carbon 1, carbon 2, hydrogen 3, carbon, that seems to double up, except what's the difference between those two carbons? One has a chlorine attached to it, the other one has two hydrogens. Is there a difference between them? Yeah, so I could star that as a chiral atom. What happens if I moved up to the other carbon? It's also a chiral atom. Okay, so in this case, I have two chiral atoms in each of these structures. Okay. So which gives us my full range of possible combinations. So between the top and the bottom, okay, are they mirror images of each other? No. For them to be mirror images, they'd both have to be the same. Okay, so they aren't mirror images, so their references S. Now I'm doing it. Diastereomer. What's the relationship between these two? Also diastereomers. Relationship between these two? Also diastereomers. Huh. These two? Diastereomers. If you organize this nice and kind of succinctly when you go through and set up your approach, you should be able to build things out and notice patterns come out of it. Have I found all of the possible comparisons?
No.
What's the relationship between these two? Take a look at the carbon backbone. Does it overlap? Exactly as drawn. Does the carbon backbone overlap? Yes. So I can slide the carbons directly on top. Do the chlorines overlap? No. The chlorine directly up, and my blue structure is dashed, and the other one it's wedged. Okay? The one to the left, wedged and dashed. The chlorines don't overlap. Do whatever you want. Spin, flip, rotate, throw it upside down. You will find that you will never be able to superimpose those two images. Okay, so they are non-superimposable. Are they mirror images of each other? That's not an easy one to see, but indeed they are. Let's take this structure here, and I'm going to pick it up, flip it over. As I flip it over, this chlorine should now be where? On the left or the right of the structure? The right of the structure. Because I flipped it over, is it wedged or dashed? What happened to the other chlorine? It's going to go on top, and it's going to be wedged. Where's the mirror plane or mirror image? If we draw a mirror right there, what would it look like? Our upper left structure here. Those two are mirror images of each other, which means the relationship between them being non-superimposable and mirror images, enantiomers. Which brings us to our last option. And then I promise I'll stop. Final answer? They aren't officially identical because there's two chiral atoms. They're meso. Okay? Yes, they are mirror images of each other, but are they superimposable? Yes. They are superimposable on their mirror image, which puts them in that identical category because we have two stereocenters within it. We now have a meso compound. Okay. I lied. I'm not going to quite stop there. Last one here, total possible stereoisomers, 2 to the n. Okay, where n is the number of stereocenters, or chiral carbons you have in your structure. For that first compound, how many stereocenters did we have? We had 2. So what's our possible total? 2 to the 2 is 4. How many structures did I draw? 4. You'll notice there's a -1 per mirror plane. Why do we need to throw that in there? One of those 4 that I drew was identical to the other one. So is it a unique stereoisomer? No. Okay? So every time you have an internal mirror plane, you would have to subtract 1. Okay? That can become complex, but let's cheat and look to a quick example here. How many possible stereoisomers? Draw your attention to maybe there and there. There are 2 chiral atoms. So we're looking at 2 to the 2, which is 4. Do you see an internal mirror plane?
Why are we just looking at those 2?
Because we're out of time.
No.
Is there an internal mirror plane in that structure? No. Which means how many possible stereoisomers? 4. There's no internal mirror plane. We don't have to worry about meso compounds. Okay? So we've got 4 stereoisomers for that. Would I ask you to draw all the stereoisomers for that? Hell no. Okay? What you would be predicted to do is what we just did with the cyclopentane or dichlorocyclopentane. Okay? And yeah, we are way done. I apologize for that.